If you have followed the other modules on conduction and convection, you will note that we have considered those modes of heat transfer separately. Now we are going to combine conduction and convection so that we can then develop some useful expressions that will help us in designing food processing equipment. So let's look at this concept of overall heat transfer. We will consider a pipe, and the inside radius of this pipe is Ri. The outside radius is Ro. Let's say that there is a fluid flowing inside the pipe, and the temperature, the bulk temperature of that fluid is Ti for the inside. And outside, let's say that again there is perhaps air around the pipe, and the bulk temperature of air is T infinity. The pipe itself is made of some material, let's say its thermal conductivity is K, and the convective heat transfer coefficients for the inside of the pipe, on the inside surface of the pipe, is Hi, and on the outside surface is Ho. So if we draw a temperature profile, we will start from the inside temperature. Let's consider that to be our higher temperature than outside. So there is some bulk temperature, and that drops to right at the surface of the pipe. Then if the pipe is highly conductive, there is a very little temperature gradient inside the pipe, and then there is again a temperature drop to T infinity. So we will use the approach of thermal resistance values to obtain an expression for the overall heat transfer coefficient. We can write that Q, that's the rate of heat transfer, equals Ti minus T infinity divided by RT, where RT is a combination of various thermal resistances. So let's see what kind of thermal resistances are there in this case. So RT will be equal to RT for the inside convection, that is inside the pipe, plus RT for conduction through the pipe material, and then RT for the outside of the pipe, which is again due to convection. So now we will write individual expressions for these various thermal resistances. So RT for inside convection will equal 1 over HIAI. You may need to look at the previous module on convective resistance to find how we determine this expression. Then the thermal resistance for conduction can be written as RT conduction equals natural log of Ro over Ri divided by 2 pi KL, where L is the length of the pipe. Again, you want to look at the module before when we talked about conduction to see how we obtained this expression for the thermal resistance due to conduction. The third item is thermal resistance due to outside convection, and that will equal 1 over HO AO, where again AO is the outside area. Now if we substitute all these different R values into our earlier equation, we have Q equals Ti minus T infinity divided by 1 over HIAI plus natural log of Ro over Ri divided by 2 pi Lk plus 1 over HO times AO. To obtain an expression for overall heat transfer, we will write an equation very similar to convective heat transfer. So overall heat transfer is from the inside to the outside, which includes both convection as well as conduction. So we will write Q equals UI times AI times Ti minus T infinity, where AI is the inside area of the pipe, and this term UI is the overall heat transfer coefficient, which is based on the inside area of the pipe. Now, UI is the overall heat transfer coefficient that we will need to know in designing various equipment. So we can rearrange our equation as Q equals Ti minus T infinity divided by 1 over UI AI, where just by comparison of this equation and the previous one, we have 1 over UI AI equals 1 over HI AI plus natural log of RO over RI divided by 2 pi Lk plus 1 over HO AO. So this equation here can be used to determine UI if we know all the other terms that are there in this equation. The one thing you will notice is that we defined our overall heat transfer coefficient, UI, as based on inside area. So the selection of this area to calculate overall heat transfer is actually quite arbitrary. For example, if we were to use the outside area, then instead of writing UI, we will be writing UO. And UO will be the overall heat transfer coefficient that is based on the outside area. In that case, the expression will be 1 over UO AO equals 1 over HI AI plus natural log of RO over RI divided by 2 pi Lk plus 1 over HO AO. So as you will notice on the right hand side, the items are exactly the same in both cases, but on the left hand side, if you use the U value for inside area, then UI must be multiplied by AI. On the other hand, if you used UO, which is based on the outside area, then UO must be multiplied by AO. So the overall expression then will be, if you're using UO, Q will be equal to UO AO Ti minus T infinity. Either of these two equations will give you the same value of Q. This you can see in a couple of solved examples in the textbook.